charges, capital letter Q and small letter q. Usually the charge is represented in an alphabetical term, that is Q. For positive charge, the arrow is outwards, and for the negative charge, arrow is inwards. The line where exactly it meets the curve is said to be a tangent. How many electric field lines passes from a unit area of cross section within a conductor is said to be electric flux, and it is given by this symbol. Hello everyone, I'm Rinda, Faculty of Physics, welcoming you all to Chapter 1, Session 2, and the chapter name is Electric Charges and Fields. So in today's class, let us discuss something more about the same chapter which we had discussed in Session 1. So here we are talking about electric field. So what is that electric field? You know, the field where you can find the influence of electricity, correct? So it's kind of a platform where you can feel the electric field. Okay, so that is presence of electricity is said to be electric field. So here it is like we have to consider a charge Q which is placed at a origin. Suppose if we consider this as a origin, the Q charge is placed at this point, that is origin O, in vacuum. And Q, small letter q, is placed at P at a distance R. So what is the distance? R is said to be a distance wherein there is a point called as point P upon which the charge small letter q is placed. Okay, so capital letter Q is a charge which is placed at a origin in vacuum, and there is a point P at a distance R upon which the charge Q is present. So there are two charges, capital letter Q and small letter q. Usually the charge is represented in an alphabetical term, that is Q. This Q called as a source charge. So the source charge is the main charge which will induce certain field on some other charges, and that some other charge is known as a test charge. So you have capital letter Q, small letter q, where this Q represents the source charge and this Q represents the test charge. After which the charge Q exerts certain force on this Q as per Coulomb's law. So you have studied Coulomb's law, that is force of attraction or repulsion is said to be directly proportional to the product of two charges, that is product of magnitude of two charges, and inversely proportional to the square of the distance between them was your Coulomb's law. The same thing is being applied over here. Okay, so the space or the region surrounding a unit positive charge. So UPC means it is unit positive charge. So this can be considered as unit positive charge. Okay, so the space or region which surrounds this unit positive charge, where the unit positive charge experiences certain field due to the source charge. Okay, wherever the source charge is present, surrounding that there is certain influence of the electricity, that is the neighboring of the source charges, the neighboring charges which is present surrounding the source charges will experience certain field, and that is nothing but the electric field which it experiences. Okay, so these electrical effects experienced by the neighboring charges is said to be electric field, or it can also be called as the intense of the electric field, that is electric intensity. So this is all about the experience of electric field in the surrounding of the source charge. And now next is electric field. The same thing you are continuing here. So it is defined as the force per unit positive charge. So what is electric field? Electric field is defined as force per unit charge. Force per unit charge is said to be the electric field. So this can be the formula for it. Electric field, it has got magnitude as well as direction because it's a vector quantity. Clear? Through which way the electric field lines is flowing, that is, it's passing. So it is always, electric field lines are always represented in terms of arrow from where to where, in order to know from where it's flowing to where. Okay, so here electric field is a vector quantity, and you have a force which is also a vector quantity divided by Q, that is, force per unit charge is said to be electric field. So here you have got your formula, the same thing which I have discussed over there. And what is the SI unit? You know the SI unit for force, as you had studied earlier, it is Newton, and the SI unit of charge is said to be Coulomb. So it is Coulomb. So Newton Coulomb inverse. So this can be the SI unit for electric field, or in terms of potential difference, that is potential difference which is existing between two charges which is placed at a certain distance. So it can be V by M, that is V voltage meter inverse, okay, which can be told as volt per meter. Next, we have the dimension formula for this electric field. How do you get this dimension formula? So it is like electric field E is equal to the force is given by MLT minus 2, okay, by, so you can just give the charge Q is equal to I into T, where current I is nothing but charge transferred per unit time is nothing but the current. So you have got Q is equal to I into T in terms of Q when we take it. So now Q is what? I into T. And what is the dimension of I? That is A, and time T is, it is in seconds. So time T usually we just give it in T itself. Dimension is represented in T, whereas SI unit will be represented in seconds. So you have A into T, which can be taken above to the numerator, so that it becomes M L T minus 2, and when this goes up it becomes minus 1, minus 2 minus 1 becomes minus 3, and you have A. M L T minus 3 and A. This will be the dimension formula for the electric field, and this is A inverse, okay, because we are taking this to the numerator. MLT minus 3 A inverse is the dimension formula for electric field. After this, let us see the electric field due to a point charge. Due to a point charge, what exactly, how exactly this electric field behave? The force exerted on a positive charge Q placed at a P at a distance R. So there is a force which is exerted by the source charge to this test charge, okay. So the certain force is exerted on a unit positive charge which is at Q, and it is placed at P at a distance R from the O, that is origin. Electric field at P due to Q at a distance R. This is what we had discussed earlier, out of which this can be called as source charge, and your small q is nothing but your test charge. So you have got your source charge as well as your test charge. Now after this, source charge is the one which produces electric field, that is Q, and test charge is the one which experiences the electric field which is produced by the source charge. It tests the effect of source charge on Q, and this produces the electric field. Whatever source charge produces is tested by the test charge. That is the relation between the source charge and test charge. And we have that if source charge is positive, the electric field is directly radially outwards from the charge. That is, if suppose your source charge is said to be positive. So how are this field lines given? So always remember the field lines, it is represented by the electric field is radially outwards. Radially means perpendicular. So I just draw the perpendicular lines for the charge. Okay, the charge, I have encircled the charge such that I draw a radial lines. Radial is nothing but the perpendicular lines for that charge. So it is like outwards. When I just give outwards, positive is always, the effect of the positive charge is always outwards, whereas it is opposite to that of negative charge. That means here in case of negative charge, we have radial lines which is perpendicular to the negative charge, that is the other source charge, which can be called as negative, whereas here it is opposite as in case of the positive charge. That means the effect is towards the negative charge. So I just can draw towards, inwards. So my arrow changes. So here the important role is played by arrows. So remember, for positive charge the arrow is outwards, and for the negative charge arrow is inwards. That is what it is. Now going on to the next one, that is electric field due to a system of charges. So now in order to calculate the electric field, we just have that suppose if there is a point P at certain distance, and here there is a presence of Q1 at distance R1, and you have Q2 at distance R2. Okay, so this will be the test charge, and Q3 at distance R3. So this is how it is. So if you consider that the test charge is experiencing certain force from this source charge, so electric field on Q experienced by Q due to Q1. So now we have the test charge and the source charges which exert certain electric field at point P at a distance R1, R2, R3, so on it goes up till the nth term as well. So now if we just consider electric field at P due to Q1 at distance R1, it can be given as vector E is equal to 1 by 4 pi epsilon naught Q1 divided by R1 square into R1 cap. Why R1 cap? Just because in order to balance the vector quantity, because your left hand side has got a vector upon electric field, that is why if you just consider so much it will be scalar, but both the side it has to be equal. Vector quantity equals vector quantity, because of which we just put cap so that it gives the equality. Okay, so now let us consider the electric field, the second electric field. This is the first part and this is the second part. Electric field at P due to Q2 at distance R2. So it becomes like vector E is equal to 1 by 4 pi epsilon naught Q2 divided by R2 square into R2 cap. So this is all about the two electric fields. So let me consider E1 and E2. It continues till nth term, that is En. So it becomes 1 by 4 pi epsilon naught Qn divided by Rn square into Rn cap. So this will be the electric field due to system of charges. It is always due to a combined system of charges. So how can you give this in total? So it can be given as vector E in total is equal to vector E1 plus vector E2. It goes up till vector En. So this is how you calculate the system of charges, because you total all the electric fields, correct? So it can be given in general. The general formula to be given is vector E is equal to, which is common in all the cases. It is 1 by 4 pi epsilon naught. This is the one which is very common, and rest of the things varies. At least it varies in the subscripts over here. So I can just take common out as 1 by 4 pi epsilon naught, and you know, summing up of every charges is given by a summation, a term called as summation. So it is like summation Qi divided by Ri square into Ri cap. So I varies from 1 to n. It varies from 1 to n. From 1 it starts and it keeps on varying. So here is the general formula in order to identify the electric field, so which you will have to remember. It is very useful in terms of numericals from this chapter. So this is what is the expression for the electric field from a system of charges. Okay, so now we have physical significance of electric field. So what are the physical significance? Electric field is characteristic of the system of charges and it is always independent of the test charge. Okay, so electric field is always independent of the test charge. This is one of the point. And force experienced by this charge Q through an electric field is given by force experienced is equal to Q into E, because you know that electric field is nothing but force per unit charge. So force experienced will be E into Q. Force experienced by the charge through an electric field is given in this format, that is, this is the expression. That is all about the physical significance, nothing to break your head in this. Next will be electric field lines. So you got to know what is electric field, correct? In order to know the influence of the electric field, what are you supposed to do? You should know like can you see the electric field lines? No, it is just the invisible thing which we consider that it moves away from the positive charge and it moves towards the negative charge. So this is just a imaginary concept. So in order to prove this imaginary concept, we should know like how to represent the field lines. So there is a pictorial representation of the field lines. So we will get to know from where to where it's flowing and from towards which charge it's flowing and away from which charge it's flowing. There is a pictorial representation which is taught here. That is, the pictorial representation of the electric field around the charges. The charges can be two charges, as I told you. It can be positive charge or else it can even be the negative charge. So we have positive charge and negative charge. Path in an electric field line which is straight or curved. Either the path can be straight path or else it can be curved path, okay, to which if you just draw a tangent. So what is meant by a tangent? Tangent is nothing but, if this is a circle, if you just draw a line, this part is said to be a tangent because the line where exactly it meets the curve is said to be a tangent, correct? So here, if we just draw a tangent to this curved line or a straight line, what happens? At any point, it gives the direction of the electric field. So suppose if your curved line is in this manner, so if this is represented as A and curve other end is represented as B, and if you draw a tangent to this curve, so it can be, this is one tangent, this is other tangent, and this is other tangent. So this arrow marks gives you the direction of the flow of electric field, okay? If suppose this tangent point is said to be P and Q and R, so this electric field is said to be E base P, and this is E base Q, and this is E base R. So here you have got, this is the direction of the field lines which passes from point A to point B. The same way, here you can see the tangents which is drawn over here, so that we got to know that it passes in this manner. So path in an electric field lines which is straight or curved such that the tangent drawn to that path gives the direction of the flow of electric field, okay? So next can be, how does the electric field behave? It is like electric field is said to be stronger near the charge. It is always stronger near a charge, and the density, if the density is more near the charge, then it is said to be stronger, and if it is less dense, then it can be called as it is weaker. Electric field is weaker when it is away from the charge, okay? So that is all about your strong and weaker part of the charges. And next it is like the field lines. Let us just represent the field lines around a single positive charge, okay, which is said to be radially outwards. Suppose if you consider a single positive charge, how is the representation of the electric field lines? It is just, if this is radially outwards, that means all are perpendicular to each other. So it is just giving outwards. For the positive charge, the field lines are radially outwards. Suppose if it is negative charge, what happens when the source charge is a negative charge? So if you just consider a negative charge, it has got radial inward direction. So this can be inward, which is radially inward direction. Next is the field lines around a system of two positive charges Q and Q. So there are two similar charges. Till now we had considered just one single charge while representing. Now we are considering two different charges, which is known as Q and plus Q. So both are the positive charges. So what happens to its field lines? It moves away from the positive charges. So I can just represent all the field lines are, the direction is away, which is given by these lines of forces. It moves away from the charge. It never attracts the other charge because like poles repel each other. Unlike poles attracts each other. Since these are like poles, it's no attraction given over in the space. So it is just repelling each other. Now it is when you consider unlike poles. So field lines around a negative charge and a positive charge or a dipole. Dipole means the one which is having two charges with different signs, positive and negative. So here we are considering one positive charge and a negative charge. So here it is plus and here it is minus. So how is the field lines of force to this? So we have the one which attracts. So like poles repel each other, unlike poles attract each other. So you're just giving certain field lines in this manner. The lines which occupy larger areas is being given by this breakage of lines. So now it is time for us to get into the important concept, that is placing the arrow marks. So how is the representation of arrow marks here? As I have told you, it is always towards the negative charge and away from the positive charge. So towards the negative charge, in the sense, the lines which is passing, I can just draw the arrow mark towards the negative charge. So it means towards the negative charge. Okay, there is an attraction towards negative charge. This is towards. So where exactly the negative charge, for that we have to draw the arrow mark. It's moving towards. Now for positive charge, it means it is away from the positive charge. So this direction I can just give it as away from the positive charge. So you can just see drawing towards negative charge resembles it is away from the positive charge and it is towards the negative charge. So this is all about the representation of the field lines on the charges, positive, negative, or in the dipole charges. Okay, so that is all about the pictorial representation of the electric field lines. Next you have field lines. How does it start? So field lines always starts from positive and it always ends at negative. It is like from positive to negative, and the arrow mark also resembles in the same way, away from the positive towards the negative. Okay, so that is all about the properties of the field lines, which is very much important. So you will have to know the properties of electric charges as well as the properties of electric field lines from this chapter. So field lines are continuous curves without any break. See the previous slide, you can see just I have broken. It is just the continuity. There is no breakage of any electric field lines. It shows the continuity of the electric field lines. Okay. So you have got the rest of the two along with this point. So one is starts at positive and ends at negative. What starts at positive? That is electric field lines. Okay. And second one, the electric field lines, that is the curves, are said to be continuous without any breaks. And third one, it is electric field lines represents the direction of the electric field. Okay, the tangent which is drawn to that electric field line represents what? It represents electric field of that particular charge. Next is two fields never cross each other. There is never crossing of any two fields with each other. So that will be your fourth point. Fifth point is it doesn't form any closed loop. Electric field doesn't form any closed loop. Okay, it is just which connects the charge, one charge to the other charge, but there is no formation of any closed loop in case of electric field lines. And the last property is electric field is always normal to the surface of the conductor. So if there is a surface of the conductor, it acts always normal or in a radial or perpendicular way. So normal, radial and perpendicular, three are one and the same, that is, it is at 90 degree. So how does the electric field line passes? It is always normal to the conductor, and this is one of the main important concept, that is the important line to be noted down, because it is very useful for the further applications of this chapter. Okay, so this is all about your properties of electric field lines. And going on to the next concept, it is the pictorial representation which I had drawn earlier. The same representation is given over here about the electric field lines. After this, we are just moving to electric flux. So what is meant by a electric flux? It is nothing but the strength of the electric field at a point when a number of field lines crossing certain area of cross section. Suppose if you consider a conductor, and this conductor has got certain area, I'll just consider unit area. This can be a unit area from which n number of electric field lines is passing over it. So this can be called as electric flux, which is given by this symbol. Okay, so it is a strength of the electric field. How many electric field lines passes from a unit area of cross section within a conductor is said to be electric flux, and it is given by this symbol. So next, coming to the same electric flux, like let's see how the flux formula is being given. That is, if S be the surface of a conductor which is divided into large number of surface element and each having the area ds. So if this is a conductor which is having a surface elements like ds can be one of the surface element area. Each area has got ds on the surface element of a conductor. Let theta be an angle between the direction of the field and normal E cos theta is component of intensity along the normal. So suppose if you consider there is a conductor with ds element and all the electric field lines are normal to the surface of the conductor. Okay, so there are electric field lines which is passing through a conductor which is having a element ds, that is surface element, within which there is a area called as ds or a delta s from which the electric field line passes through it. So when that is the case, if suppose a little bit the conductor is being tilted, what happens? Tilted by an angle theta. That is, so let theta be the angle between the direction of the electric field and the normal be E cos theta. And that is given as, if suppose this is a electric field which is passing and this is just a tilting of your conductor at an angle theta. So when you just draw a normal to it, it makes an angle theta to this tilted angle over here. So this is at 90 degree, that is theta. So let theta be the angle between the direction of the electric field and normal E cos theta is a component of intensity along the normal. So it becomes E cos theta. Remember, theta is the angle, that is a tilted angle. The electric flux through the surface element ds. So suppose if there is a surface element ds, how can you give the flux through that surface element? And it can be given as d phi is equal to E cos theta, that is this part, into the surface element area of the surface element ds. This is how you give the electric flux formula. So I hope you understood. When there is a conductor over here and the electric field intensity is always normal to the conductor, which is given in a general form in this way. And suppose if that conductor is tilted slightly such that it makes angle theta and it is at 90 degree from the tilted angle, then you have got d phi is equal to E cos theta into ds. That is all about your electric flux. Next, coming on to electric dipole. I've already discussed what is meant by a dipole. Dipole means it is two poles. Okay, so here pair of equal and opposite charges which is separated by certain distance is said to be dipole. So equal and opposite charges. So suppose if there are two charges Q and Q, because it is equal, and opposite charges, so one can be plus and one can be minus, which is separated by a distance, certain distance, let's say it is r. So it is separated by certain distance r, then it is said to be a dipole, or two different charges which is having equal and opposite signs. Okay, so it is equal and opposite charges separated by certain small distance is said to be electric dipole. So this is one of the easiest definition, correct? So now let us see what is electric dipole moment. So dipole means the two charges which is separated by certain distance, correct? So here something more is added to it, that is, it is a vector quantity. Remember, the dipole electric moment is a vector quantity and the magnitude is equal to product of magnitude of either charges and distance between them. So you know, dipole plus Q and minus Q. So this is the dipole and the distance between them together it is known as dipole. So dipole moment means it is product of two. Okay, so magnitude is equal to, that means the value of dipole moment. Usually the dipole moment is represented by P vector. Okay, vector P means it is a dipole moment. It is a vector quantity which has got certain direction, and I'll tell you like how it moves. So it is a dipole moment which is represented as the magnitude is equal to product of magnitude of either of the charges. So it is just concise to one single charge irrespective of its charges, that is irrespective of the positive or the negative sign. It is just considered as only the magnitude of either of the charges. So it becomes Q and distance between them. Suppose if you are taking it as 2a, the distance between them can be considered as 2a. Q into 2a. So it is Q into 2a into P vector, because just to balance this vector you just write it as P vector in order to balance your left hand side. So this can be the formula for electric dipole moment, and remember, electric dipole moment is always from negative to positive. Don't get confused with positive charge, that is field lines, and dipole moment. The field lines are always moving from positive to negative, whereas dipole moment is always shown from negative to positive. That is just opposite of the electric field lines. Okay, so now you have got two dipole charges, that is dipole. What is that electric dipole? Two equal and opposite charges which is separated by certain distance, wherein the charges can be zero but the electric field between those charges can never be zero. So that is all about your electric dipole and dipole moment. So I hope you're clear with these things. So now having these, the field of an electric dipole, we will have to check the field of an electric dipole. So in order to check its field, we just consider two kinds of section, that is the electric field E at a point P, at a general point which we consider as point P, is obtained by adding two electric fields, that is E1 and E2. You can even consider this E1 and E2 as E positive and E negative due to plus Q and minus Q in the parallelogram law of vector format. There are two derivations, that is the result of electric field at point P can be obtained on the dipole axis as well as on the equatorial line. So there are two things. One is on the dipole axis, the other one is on the equatorial line. Coming to this dipole axis, that is electric field at a point on a dipole axis, it is nothing but, suppose you consider a electric field. So just consider a dipole. So there is a line . So here you have minus Q, here you have plus Q, and there is a point P which experiences electric field, and this is E1 and E2, and there is a center that is called as O, and the total distance of this is called as 2A. That means divided distance is A and A together, it is called as 2A, and point P is at a distance R from O. So this will be the general and the initial step which we will have to take up in order to derive this, and this is one of the most important questions which comes for 5 marks. Okay, so here we have got the setup, the complete setup, like how exactly we have to calculate the electric field at point P due to the dipoles which is present over there. Okay, so this is a general concept. Now starting from the electric field at point P due to positive charge and the negative charge, and remember the one main thing is like the dipole moment. I had already told you dipole moment is from negative to positive, so I can just give an arrow mark along this line and give P vector which is said to be the dipole moment, where plus Q is positive charge, minus Q is said to be negative charge, P is a point on which the electric field due to dipole is observed, and 2A is the distance of separation of two charges. Okay, and vector P is the dipole moment. So these are the basic concepts. Now we have to calculate the influence of electric field due to dipole at point P. So first of all, electric field at P due to plus Q, let us see that. So first one, electric field at P due to plus Q, that is positive charge. So I can just give it as E vector and plus is equal to 1 by 4 pi epsilon naught Q, that is plus Q, divided by R square. Usually general formula is R square, that is distance between them. So I'm just considering from here to here, and this is nothing but you're just minusing, you have got 2A, you're just minusing 1A with that. So it is like R minus A. This complete is nothing but R. You're minusing this A from here. This section you're not taking. So it is R minus A. It becomes R minus A the whole square. Okay. So that will be the total distance, because you're considering the distance of the dipole. But plus Q is acting on P first. First of all, you have to consider only individual charges and then you have to sum up in order to represent the electric field influence at P due to both the dipoles. So here you have considering only one of the charge, that is positive charge first. So 1 by 4 pi epsilon naught positive, that is plus Q, have not taken plus, divided by R minus A the whole square, and it can be equated, so it is nothing but P cap, just in order to balance the equation. Similar way, if you just consider electric field, this is the second one, due to minus Q at P, so it is like E vector minus, so it due to the negative charge, so you have got 1 by 4 pi epsilon naught Q divided by R minus A the whole square. So here you're considering minus, that is a negative charge. From R, you have to add this also, this distance also. So it is R plus A. So I can just write it as R plus A the whole square, and balancing minus P cap, because it's a negative Q. Minus Q, I have taken my minus over here along with P cap. So these are the two electric fields. One is due to positive charge plus Q and other is due to negative charge minus Q. So now the resultant electric field is combined, that is summing up of E plus and E minus, you get the electric field due to the dipole axis at a point P on a dipole axis. So now let us sum up these two equations. Summing up these two equations becomes vector E is equal to E1 plus E2. So it becomes 1 by 4 pi epsilon naught into, taking 1 by 4 pi epsilon naught outside, and what remains is Q divided by R minus A the whole square into P cap minus Q divided by R plus A the whole square into P cap. So this is how it goes. So your P cap will be common terms over here and Q comes out again. So Q divided by 4 pi epsilon naught into 1 by R minus A the whole square minus 1 by R plus A the whole square into P cap. This is the equation vector E. So taking the common out and LCM, it's like 1 by 4 pi epsilon naught. You have got R plus A the whole square minus R minus A the whole square divided by R square minus A square the whole square into P cap. On solving these two equations with the help of A square plus B square plus 2AB and A square plus B square minus 2AB formula, applying for these two equations, you will end up with Q by 4 pi epsilon naught into 4AR divided by R square minus A square the whole square into P cap. So you know that dipole moment P is nothing but charge Q into 2A with P cap. So this is your dipole moment. So same dipole moment can be induced over here, that is 1 by 4 pi epsilon naught, your Q and 2 from this 4 and A, Q, 2A and P becomes dipole moment. So I can just give it as vector P into R divided by R square minus A square the whole square. So here 2 is remaining, so I can just add 2 and this can be the equation to give you the electric field at a point on a dipole axis. So suppose if you consider your A is very much smaller than vector R, then it becomes like, when you just cancel this, it becomes R cube. So in this equation, what remains is E is equal to 1 by 4 pi epsilon naught 2P divided by R cube will be your final answer when you consider A is much smaller than that of the R. Okay, so that is all about the electric field at a point on the dipole axis. So in today's class, we have studied about the electric field lines, its pictorial representation, properties, as well as electric field at certain point on the dipole axis. So that's all for today. Let us all meet in the next session, that is session 3 from the same chapter. Until then, have a good day. Thank you.